again, a process based on solvent extraction, using all the theoretical elements we have just gone through, for the separation of uranium, plutonium, and fission. First, I'm going to give a brief introduction to this, just to show where we start and why this is needed. But we have seen most of this as part of the nuclear fuel cycle lecture, so that would be a brief review. So why do we need to reprocess the nuclear fuel? So we are now at the point in the cycle where the fuel has been used in a reactor for a certain time. The times are given here, can be 3 to 5 years for thermal reactors run uranium, and 18 months for fast reactors. After that time, there are two issues. First, there are some physical changes that affect the properties of the fuel. So that's some aging, basically. And secondly, the reactivity of the fuel itself decreases, not because the amount of uranium drops to a very low level, but because fission products like xenon and iodine and several others appear in the material, and they are active in capturing neutrons, so they drop the efficiency, the neutron efficiency of the fuel. So these are reasons why, even if there is uranium-235 there, the fuel needs to be taken out of the reactor, reprocessed, the uranium recovered from that fuel, and then the rest of the products disposed in one way or another, as we will do this. What are the other products? Well, typically you have baryon, krypton coming from uranium, then you could have also some reactions of uranium-238, and typically what you will end up is with a large amount of fission products, as well as plutonium and uranium of the same type. So this is what needs to be split. The actual proportions will be different for, well, depending on the type of reactor and depending on how long it's been operating, and depending on whether it was fast reactor or a thermal reactor, because the balance of neutrons changes between them, so the product distribution is different. This is a typical distribution for pressurized water reactor, and you can see it contains a number of fission products there and various concentrations. So these are typically the type of products, these are the elements we want removed from the fuel. So we want a stream which contains them, another one which contains the uranium in its two forms, 235 and 238, and a separate stream for the products. So in the process we're going to see, after reprocessing, what you have is waste, which is the fission products. You have another stream which contains uranium, both 235 and 238, because solvent extraction, as you can guess, as you have seen, cannot distinguish between them. They have the same chemical behavior. There is no big difference in the affinities for a kerosene phase, depending on whether it's 235 or 238. So that can go again to an enrichment process that you have seen. But from this separation, they are recovered together. So all the uranium goes together. If further enrichment is needed, then we'll need to go to a centrifuge or diffusion stage, whatever is used in the plant, but not in but it's not separated at this point. And the third stream is what? Well, the third stream is the plutonium that may have appeared in the reactor, and obviously the proportions will change from thermal to fast reactor. So the reprocessing strategy is one followed by the UK, among others, and involves this separation. The alternative is to just dispose the full assembly without recovering any uranium or plutonium, which is what some countries as well have gone. So the objectives of reprocessing is, well, first, recover plutonium. As I said, there will be a stream containing plutonium, and that has to be, basically we want to recover as much plutonium as we can from those, so doesn't go to waste in the fission products or doesn't end up with uranium. A small, it has to be, that plutonium has to be relatively pure, so with a very small uranium content in it, and also with a very small amount of fission products, right? So we're looking here at two slightly different things. The second and third bullet point here refer to how pure the plutonium that we are obtaining. The first refers to how much of the original plutonium we can recover. And as you can see, they may be going in opposite ways. So the more plutonium you want to recover, the less the purity, or the purity can be affected negatively.
I forgot the number. I was trying to work out how much plutonium-239 is left in spent fuel.
Well, that's
you know, an average PWR.
Well, I think I have some figures later, but well, it really depends on whether you are talking about weight or radiation. So, on radioactivity, in radioactivity, it is mostly it comes from the fission product. So you have 95% of the radioactivity from the fission products.
I mean in terms of the by weight, yeah.
In weight, it's very, very low, much fewer than 1%, and we can be talking about not
the fission
1%.
product, the fission products.
No, the plutonium.
Oh, okay.
Yeah. So, yeah, basically, the split is most of the spent fuel, 90-something% will be uranium. You have an amount, again, there is a range there. It's normally less than 1%, but it can go for 1% of up to that figure of plutonium. The fission products are a small amount by weight, but they account for most of the radioactivity of the material. Right? So, really, that's why we are giving here this purity is given mostly as productivity, radioactivity of the fission products in the plutonium, rather than as weight, because the weight is very small to start with. Well, and there are similarly similar targets for uranium. So you want to recover the depleted uranium in a pure form, and you want to recover as much as possible. The fission products will go to a form that is suitable for permanent storage, and you will see more about that in the coming 2 weeks. And of course, all this has to be in a very controlled and safe way. It has to be any emission to the atmosphere has to be controlled. There are some, as we will see, elements that are emitted to the atmosphere. You may remember we discussed this. So the first step is a cool down period in a cooling pond, where the fuel as it came from the reactor is placed. So here you can have rods. This is covered by water, which will absorb any radiation. And this is left there for a few years, 3 to 5 years typically. And you can see that by that time, there is a considerable decrease in the radioactivity. So if you look at this logarithmic scale, so if you look at 1,000 days, about 3 years, you will have decreased the radioactivity by a factor of 100. So there is a large drop in radioactivity over that period. So these are some general principles of the Purex process. Of course, needs to be designed for a required throughput, how much input is going to have in, say, kilograms per year to be processed. Losses of uranium and plutonium to waste stream have to be low, start low. Of course, needs to be safe in terms of any risk of criticality. And the contact time, then they have to be short. We haven't spoken much about residence times. I'm not going to go into that in detail. But basically, this is the time in which the two solutions are put in contact to reach equilibrium. So you want that to be very close to equilibrium, but you don't want them to be very in contact for a longer time than needed, as there is some degradation of the TBP in the solvent that may occur. So let's go at the general diagram. So when the fuel from the storage pond is treated, there is a first step which is open the rod, open the cladding, and that will release gases that will go through a treatment. Some of them can be released to the atmosphere. And then there is a very important first step, which is the dissolution in nitric acid. Right? So this is where the process related to the solvent extraction starts. Right? So as you can see in all our examples, we were saying, well, this is an aqueous solution. It may contain some acid. Well, that comes from there, from dissolving the fuels into nitric acid. It's an aqueous solution. After that, there is a primary decontamination. What happens here? Well, this is a first solvent extraction process, which may consist of a few stages, 3 to 5, and in which fission products are removed, and it achieves a very high removal of the fission products. So what is left? So one stream is the fission product. What is the other? Uranium and plutonium will be separated, right? So this is our waste. The rest will be reprocessed. So we will see that there are two different streams, one for plutonium, one from uranium. So they are separated them in further stages from ammonium cells, and they will be fed again to the cycle, to the nuclear fuel cycle. Can anyone tell me, for example, why this is a fluoride? Does anyone remember that? Where was a fluoride used? Why do we want the output in terms of uranium via fluoride?
In the enrichment state.
In the enrichment, that's right. So because this stream is going to go back to enrichment, obviously it's been depleted in uranium-235. It needs to go back there and go through the enrichment process, and that is where then the uranium is fed again to the cycle, right? So this will go through enrichment and then preparation of the rods and another time in the reactor. Right, so let's look in more detail at what happens in each of these stages. Let's start with the dissolution. I don't mean that you need to know these reactions, but just for general information, what happens is that the uranium is going to form some nitrates, and some gases are going to be formed as well in the process. So this is the solution. So this is a soluble salt. So this is in water. So now we have the component in water ready for separation. Plutonium is again converted to plutonium nitrate. And note here, because this will be important later in our discussion, what is the oxidation state here? This may be a very chemistry-like question, but so you remember from a chemistry course or A levels or something of that sort. this is plutonium in oxidation state 4, and we will see that that has an effect on the separation, right? We will see that one of the bases of the separation is to change this oxidation state, because if you change that oxidation state, then the affinity, the relative affinity for the active phase and the organic phase is going to change. More about that in a moment. So, the fuel is dissolved in nitric acid, and it goes through a first primary decontamination. So again, primary decontamination is a separation, uranium and plutonium on one side, and fission products on the other. Now, let's look at these distribution coefficients, and let's think what we can do to help this separation. So, what would you do in terms of the plutonium, just linking with what we were discussing earlier? So, do you have here plutonium in oxidation state 3, oxidation state 4, and oxidation state 6, right? Which is the best one for our purposes? 4. Why? Yes, you have a large distribution coefficient, so there will be 20 times as much plutonium in the kerosene phase as in the aqueous phase. And we want that because the fission products have a very high affinity for the aqueous phase, right? So most of them will remain in the aqueous phase. And of course this can be improved by several stages there. So with plutonium there, so we will want to have that in oxidation state 4, and that's something that can be controlled, making it react oxidizing it to that very precise oxidation state. So you don't want to over-oxidize it to stage 6 because this is not so good. And you want definitely to avoid oxidation state 3 because then plutonium tends to stay in the organic phase. So this is an important thing. You can change the affinity of plutonium by changing the oxidation state. That's the bottom line. So, do you know any way of changing the affinity of uranium? This table doesn't say much. It just gives a number of 30, which looks good. It's even higher than the best we have for plutonium.
Decreasing the pH.
Yes, so the acidity has an impact on this. So as you have an acid solution, remember that we are coming from the solution in nitric acid. So that, again, having the acid there helps this distribution and having a large distribution coefficient. Okay, so you can compare that with the distribution coefficient for some typical fission products. Again, for example, for cereal, you will have only 2% of the cereal going to the kerosene phase, right? This is again further helped by having TBT, which will stabilize uranium in the kerosene phase. Right, so we got rid of the fission products in that way, and now we are going to do uranium-plutonium partitioning. So now the separation needs to be between these two. Before we just group them and move them to the kerosene phase. Now tell me what we can do then here. So how do you partition now uranium and plutonium? Let's look again at these numbers. What can we do now that we have, from the previous stage, we have uranium and plutonium in a kerosene phase. What happens next? What do we do?
Change the oxidation state.
We change the oxidation state of plutonium. What will you change it to?
To 3.
3. So what happens then? Plutonium will have a much higher affinity for what phase? For the aqueous phase, right? So in this case, you can, by doing that, move plutonium into the aqueous phase. this is exactly what is done. Again, this is some perhaps more detail than what you need in terms of how it is done, but basically we move from oxidation state 4 to oxidation state 3, and that enables the separation. So plutonium will go to the aqueous phase and uranium will stay behind in the kerosene phase. How about the acidity? What do we want to have here? A low or a high pH in the aqueous phase? So where do we want uranium to be? The kerosene phase, right? So, because again, this shows that we are extracting plutonium into the aqueous phase. So uranium will stay in the kerosene phase, and that is favored by what? In terms of the acidity.
Low pH.
That's favored by a low pH. So if you have an acid aqueous phase, then of course that means low pH, and the uranium will tend to stay there. So you are not changing, you are not decreasing this coefficient. Right. So after that initial partitioning, there are further stages that have to do with the purification. Because you have that first separation, but then there will be some plutonium that stays in the stream, there will be some uranium that stays there, small amounts, but you want to recover and improve the purity of each of the streams. So this goes through several cycles, and you can do the same thing again. So you can cycle, now plutonium-3 is oxidized again back to plutonium-4 and extracted in the organic phase, and by doing these cycles you can improve the purity of plutonium. Of course there is a trade-off here, because the more you improve the purity, the more plutonium you may lose. So there is a trade-off between efficiency and purity, as we mentioned. And for uranium purification, again, this is based on changing the pH of the solution. So when the pH is increased, then you can extract back uranium to the aqueous phase. Right. So, just to summarize what may seem a complex process, but we first separated the fission products into the water. Uranium and plutonium stayed in the kerosene. How do we manage to separate uranium from plutonium? Well, for plutonium, we play with the oxidation state, and for uranium, we play with the pH of water. So those are the main controlling ways of adapting the system for uranium. So by doing that, we are changing M, and as we know, changing M, we can control the separation. And so then for a given M, we can calculate in the ways we have done number of stages, and then you can achieve any degree of separation you want. So this is just some numbers on the distribution of uranium as a function of acidity. So again, this gives you the total number. This is basically M, which sometimes is called dB for distribution coefficient. But so you can see here how the more the acidity, so the concentration of nitric acid, the higher the distribution coefficient, which means uranium will escape towards the kerosene phase. There is another interesting thing, which is uranium distribution versus uranium loading, right? So how do you read this one? The distribution coefficient goes down when what happens?
When the enrichment increases.
This means that you have more uranium in the system. So, in other words, our M is a function of X, if you want, right? So we are in that case. this is the change of M as the concentration of uranium changes. So the larger the concentration of uranium, the smaller M is. So you can extract a lot of dilute solutions, but if you have a concentrated solution, well, the distribution is not so favorable. So you maybe better off diluting it in terms of the equilibrium. Yeah. So again, that's another angle, but it's certainly another handle that we have in the system, certainly good to increase the purity of those later things. Well, this is the full thing. If you look in detail in this slide, I'm not going to go into a lot of details, but you will have here all the components. So this is the primary decontamination, where the fission products are recovered, and then the stream containing uranium and plutonium goes to further partitioning. So you can see there are various stages. Each of these, there are various steps, I would call it. Each of these steps, each of these columns will have several stages, all right? And between these steps of the process, you can change some conditions. For example, let me try to find one here. You have plutonium as +3, and at the exit you have plutonium as +4. That is because it was oxidized here at the entrance to the column, so you favor the separation. So again, this is not new. This is just a more complicated flow sheet of what we've seen in the previous slide, but this is just containing all that info, right? So the next thing is what happens to the just to close the thing, we shown this before. The waste can be vitrified. Again, you will have a dedicated lecture to this next week. And then stored in geological formation, that's for many years. And what you can see there is the time it would take to the radioactivity to reach the radioactivity of the original ore, where uranium was extracted at the beginning of the nuclear fuel cycle. So the original occurring ore, so the rock where uranium is, to reach that radioactivity, if you don't do any reprocessing, so if you put back all the uranium 235, 238, plutonium and fission products, it would take 10,000 years to that to go back to the original state where you have the radioactivity that you could have in a mine. By removing uranium from the waste, so by removing uranium only, so not doing anything to plutonium, just sending it for permanent storage, that period is reduced to 1,000 years. And finally, if you consider what we could call full reprocessing, so you only have 0.5% of uranium and plutonium in the waste, then that can be brought down to 500 years. So this is the impact of reprocessing on then the final storage conditions, right? Of course, there is something else apart from the safety of the thing. Certainly, well, we're talking about very long times anyway, but certainly 500 years is probably a bit more predictable and controllable than 10,000. So you can see things as old as 500, 1,000 years around the country. I'm not sure about 10,000. But in any case, the other important advantage is that you have fuel. Well, obviously, it's not just from the point of view of decreasing the radioactivity in the waste, but also, while we took out of here the uranium and plutonium that were removed, are again available as fuels, and as we have seen, they go back to the nuclear fuel cycle. Right, that was it for this part. There are some references where you can read more about this, and some of the figures were extracted from the investment from Benedict. I'll give you another 5 minutes, and then you have to do some work. We are going to just solve some problems on solvent extraction, where we have 2 solutes, and we need to reach certain supermarkets. So this is the problem. Let's start in 5 minutes.